This is an introduction to eigenvalues. Let A be an m by n matrix. For example, A could be a 2 by 2 matrix, let's say 1, 1, 2, 1. Now a scalar, which is a real number, okay, real number, is called eigenvalue of A if there is a non-zero vector. Okay, I highlight non-zero vector V such that A times V equal lambda V. So for example, this means that for example, if my A is 1, 1, 2, 1, then there's a vector V, let's say A times V equal lambda V. And this lambda is called eigenvalue, and this is what we are after for this lesson. The vector which is non-zero is called eigenvector of A. They are all associated to vector with a matrix A. So for example, in this case, A is 2 by 2, then we expect A times V, let's say x1, x2 equal to lambda times x1, x2. For this lesson, of the following example, we are trying to figure out what is lambda here. Okay, so not all the time the matrix A may not have any lambda, but most of the time we are given a question which you can find lambda here. So some remark here, the eigenvalues and eigenvector can be complex, but we are restrict them to real number. So don't need about real complex eigenvalue and complex eigenvector. So I want focus on the real eigenvalue and real eigenvector. Okay, this is point number 1. Point number 2 is if you have an eigenvector, any multiple of eigenvector is also an eigenvector. So for example, suppose you have A times V equal to lambda times V. So V is an eigenvector now. So now how about A times mu V? A times mu V is a multiple of V now. You can take out mu here, okay, A times V. So A times V we know is lambda V. So A times V is lambda V here. So this is actually mu lambda V now. So you will find that, okay, I push the mu inside and bring lambda outside here. And then this is actually lambda times mu V. So you find that I have mu V is eigenvector now of A with eigenvalue lambda. Okay, so mu V is an eigenvector of A with eigenvalue lambda. So for example, if V if an eigenvalue here, for example, if V is eigenvalue here, so for example, if V is eigenvector of A, then 2V is also eigenvector of A. Okay, so where you take mu equal to 2 now, okay, mu equal to 2 is also eigenvector of A. Third point, we never consider zero vector an eigenvector of A. This is because if v is 0, a times 0 also 0, which is equal to lambda times 0 here. So therefore, we don't consider this because anyway, a times 0 is equal to lambda times 0. So it's obvious, and this is meaningless here because a times 0 now. 0 is if 0 is eigenvector, you still get lambda times 0. So 0 is always vectors a times 0 equal to lambda times 0. So for any lambda here, so that is why we don't consider 0. It's obvious. So we will look for non-zero vector. Okay, that's why you look for a non-zero vector. However, it is possible to have lambda equal 0 if happen. Okay, however, it's possible to have lambda equal 0, although v cannot be 0, right? Lambda can be 0. So this is the first introduction of eigenvalue. Example 17. Given a matrix 2, 0, 0, minus 1, verify that 1, 0 is an eigenvector A corresponding to eigenvalue 2. So what does that mean? So let's analyze the question. So I have a matrix A now. Verify that 1, 0, V1 is an eigenvector of A corresponding to eigenvalue lambda equal to 2. Which means that if you analyze the statement, what is the eigenvalue here, means that you want to show that A times lambda V here, A times V here, supposed to be 2V now because lambda is 2 now. And V is actually 1, 0. V1, alright? V1 is 1, 0. So let's try to prove it. So A times V1, which is equal to 2, 0, 0 minus 1, times V1 is 1, 0. So you multiply the matrix here. So 2 times 1, 0 times 0, you get 2 here. And then another one, let's say 0 times 1. Okay, so 0 times 0 here, sorry. So 0 times 0 here. So you get 0 times 1 first. Okay, 0 times 1. Sorry, okay, sorry. Okay, I have 2 times 1, 0 times 0, you get 2. And then the next column here, the next row here, it has, that's right, 0 times 1, 0 times 1, minus 1 times 0, you get 0 here. So that is finish the first column. Now I look at second column now. No more second column really. Actually, it's the result is actually 1, 0. So this is 2, 0 now, which is equal to 2 times of 1, 0, which is 2 times V1. So we have shown that A times V1 is equal to 2 times V1. So therefore, 1, 0 is an eigenvector of A with eigenvalue lambda equal to 2. So if that is the case, because I say the word here is an eigenvalue because it's an eigenvector here and eigenvector. So there are many eigenvectors. So for example, if you take 2, let's say 4 times 4 by 1, 0, okay? So you take 4 times 1, 0, which is 4, 0 here. is also an eigenvector. Okay, you can check that A times 4 0, you'll get 8 0, which is equal to 4, 2 times 4 0. Okay, check. Okay, you can check. Now, let's look at another statement. This one. Show that V2 1 is an eigenvector A corresponding to eigenvalue lambda equal to -1. So we do a similar things. A times V2 now. A times V2, which is equal to 2 0 0 minus 1 times V2 is 0 1. You multiply out, you get 2 times 0, 0 times 1, you get 0. And then 0 times 0 minus 1 times 1, you get minus 1. So this is actually minus 1 of 0 1, which is equal to minus 1 of V2 now. So you find that A V2 is minus 1 V2. That means that V2 is which is 1 0 0 1 is an eigenvector of A. Okay, with eigenvalue lambda 2 equal to minus 1. Okay, so let's see what else I will emphasize. First, the eigenvector V is never 0 0. So 0 0 cannot be eigenvector because I will mention this V must be non-zero. So you happen to get V is 0 vector, then you make a calculation error already. So this is the end of this example 17.